Hi everyone, this is Vishal. In today's video, we are going to enhance our Gmail design a little bit further. We asked a various clarifying questions to our interviewer. We reduced the scope of the problem. We designed the APIs and then we estimated the storage as well as QPS for our Gmail design. Now, we'll take an example, we'll take a functional use case and then design the system further. Imagine there is a Gmail client, that's a user A, that is sending an email to two users. Let's say B is the receiver and C is in the CC. So a Gmail user could send an email to two users. One could be another Gmail user B and another Outlook user C. Now imagine this is a use case where a Gmail user sends an email to another Gmail user and another Outlook user. Having this functional use case in our mind, we are going to design the system for Gmail. Now let's look at a very high level what could be the component diagrams for the backend systems for Gmail. Okay, so let me pull it a little bit above so that they don't merge. Yeah. So when the Gmail client A, the A user sends an email, what is the first thing he or she does? He or she writes the email and clicks the send button. Where does your email goes to the very first place? It first goes to your Gmail backend send service. Now this service is responsible for fetching all the emails that have been sent by the clients. So the client A sends an email. This backend service fetches all those sent emails. Now this Gmail backend service that catches all those sent emails passes over those sent emails to the receiver services. Now we could have a receiver service at the Gmail end and we could also have a receiver service at the Outlook end, right? Because we are supposed to send our emails to two users. One was a Gmail user and one was an Outlook user. Now from these receiver services, our clients are actually listening the new received emails. So B is also listening for the new received emails and C is also listening for the new received emails. The reason I have listed A as well is because once A has sent the email, we need to update its sent folder as well. So if you look at a very high level, what happens when a user A sends an email? When a user A sends an email, let's say the user was from the Gmail service. So first the Gmail backend will receive that sent email. Then the Gmail backend will pass on the email to receiver services on both the Gmail side and the Outlook side. And the clients, let's say in our case B and C, will keep listening from these receiver services for the updated emails they are supposed to receive. The reason we added A here as well because we wanted to update the sent folder for the client A as well. So once A sent an email, B and C users will be able to see the new email in their inbox, whereas A will be able to see the new email in its outbox. So at a very high level, this is how emails are transferred between clients. And we have taken a complicated case where the sender and receiver belong to two different email services, one from Gmail and one from Outlook. So what we will do now is we will dive deep onto the backend service separately and the receiver services separately. And then we'll focus on how the clients like A, B, and C are receiving the real-time updates of new emails they are supposed to receive. So stay tuned. these are some very important topics. So let's start with the Gmail backend service. So let me expand this a little bit. Okay, 1 second. So this is our email sending flow, and let's say, as we mentioned earlier, that there was a client A that was typing an email on its Gmail application, and he or she clicked the send button. So from this client, from this Gmail client, this packet of the email, the message which the client is sent, will pass on to what? The Gmail backend send service. And this is the dive deep on the send service, like how and what should be included in the send service. Alright. So this is what we are going to dive deep now. So when the client sends the email, this is the backend service which we are now dive deeping. So the client's message passes through a load balancer. Now we are very much aware of load balancer, like it ensures rate limiting, it ensures request routing. So what all backend servers are there at the behind of the load balancer, it controls to which server I should route my request. How should I limit the rate of my incoming requests so that my backend servers are not bombarded at all. So once that request is received at the load balancer, this load balancer passes on the request to some backend servers. Now let's call these backend servers are as reducers. Now what is the purpose of reducer here? So the purpose of reducer is that email message could have 2, 3, 4, 5 attachments, and they could be in 10 MB, 20 MB. Like each attachment, if it's 20 MB, the size of an email packet could be very huge. Now the purpose of this reducer is I want to reduce the size of my email message. I don't want to carry forward the attachment along further. I can do one thing. I can actually go ahead and store the attachment somewhere in a blob storage, something like an AWS S3. And then the reference link of this storage of the attachment, I can attach to my message, and then this referenced message is something that I pass further ahead in my system so that all my downstream services do not consume so much network bandwidth, do not consume so much storage space for this attachment. I just need to pass the reference of this attachment in all the downstream services that are there. So this reducer service just fetches those attachments, stores them to S3, reference their links into the backend that stores the email contents, and then passes them on to a PubSub model. Now, why have I kept a PubSub model here? The reason I have kept a PubSub model here is these PubSub models actually act as a buffer so that its upstreams and downstreams can be scaled independently. Let's say I am receiving a lot of requests at the reducers, and there are a lot of reducer servers I have kept here, but I don't want to scale my downstream servers to such an extent. That's why I have kept the buffer PubSub model in between so that these downstream servers can consume the messages from the queue or the PubSub at their own pace. They don't need to scale with the upstream space. They both can scale independently. The downstream and the upstream can scale independently. That's where it's very important. It's a very important design pattern to actually keep the PubSub in between two services so that they can scale independently while the PubSub acts as a buffer for them. So once we have reduced the message size, we have pushed the message to a PubSub from which some validator services backends are actually pulling those messages. So what these validators do is, these validators check the message for spams, check the message for virus, and a lot of other system business validations that are supposed to be done. If some messages are not satisfying the required validations, they are passed into the error queue, which can then further be consumed by some downstream for further processing, analytics, or any other thing. It's better to keep a Kafka here so that there could be multiple consumers. So a queue restricts you to have a single consumer, but having a Kafka topic, right, you can have multiple consumers for it, one for analytics, one for reprocessing and stuff. So these are all the messages, all the emails that have failed the validations. Now all the emails that have succeeded the validations are again passed to the message queue. And we have already explained why to use a PubSub in between two services. Now from this message queue, after we have reduced the size of the message, after we have validated the messages, now we have to perform our core task. So the user submitted this email because he wanted it to be sent to B and C. Now our core task to do is, after reducing its size, after validating it, let's send it to B and C. Now here we will not directly send to B and C. Let's say a given email has a single person who was sending that message or sending that email, but the person can send the email to hundreds of people in the two column. Let's say I send to B, C, D, E, F, G, H. Similarly, a single person can send an email to hundreds of users, right? I don't want to fan out here. So this service will not do anything. This service will just break a single email message to 100 tasks. So let's say initially I had a single email that said the sender is A and the receivers are B and C. That was a single message. Now I'll break that single message to two tasks, or let's say three tasks. So each of the tasks will be something like this. So the first task will be the sender is A, the receiver is A. Second task is sender is A, receiver is B. The third task is sender is A, receiver is C. Similarly, if I am sending message to 100 users, I'll have 101 tasks. Alright. Now, you would be asking me why I have created a task for A as well. The first task where sender was also A and receiver was also A. So if you understand something, what is the task of sending a message? So when A sends a message to B, we update the inbox of B. When A sends a message to A, sender and receiver are both same. We update the outbox of A. So for a single email, how many such update tasks are supposed to be done? Right? That are the tasks we create here. So if A is sending a message to B and C, we have to create three update tasks. We have to update the outbox of A, we have to update the inbox of B, we have to update the inbox of C. So we break a single email to some n tasks, some n update tasks we have to perform. Now all of these tasks are individually added to the message queue. So now you can say that the traffic that was there in this part of the system, now the traffic has increased a lot in this part of the system, right? Because a single email can have various update tasks. So this much traffic, this traffic is definitely more than the traffic that was there in the upstream. So we added them to a PubSub model so that each tasks, right, like updating the outbox of A, updating the inbox of B, updating the inbox of C, could actually be solved independently. Now we have added all those tasks to our PubSub model. We have a lot of consumers here. Now these consumers just pick one task, and that each task has, this is the sender, this is the receiver. Now it finds that, let's say the business logic here would be, if sender and receiver are same, just update the outbox. If sender and receiver are different, update the inbox of the receiver. So this particular consumers have this task. So what they do is they actually update those details, but they don't update those details directly, because see, the receiver could be on a different email server altogether. In our case, when we saw, the B was on the Gmail client server and the C was on the Outlook server. So they don't update the inbox and outbox directly. They actually delegate those tasks to the receive servers. So these send consumers, they they find that if the email servers of both sender and receiver are same, let's say in our case, if the task where A was the sender and B was the receiver, and the emails were a@gmail.com and b@gmail.com. So this consumer will send the message to the Gmail receive server. But if the receiver is in the Outlook receive server, it will send the message to the Outlook receive server. Definitely we will dive deep on the receive server design as well. But now you got a gist of it. Like, how have we segregated the responsibilities in our design? Now the Gmail receive server will be in the intranet of the Gmail backend, whereas the Outlook receive server, to reach that we have to go through the internet. That's why I've specifically shown it in a separate circle. So this is the entire design for our backend send server. So client A clicks the send button, we receive the message to the load balancer, we reduce its size, we validate the message for spams and viruses. For a given email, we create various update tasks based upon how many receivers are there. Then for each of these tasks, we see if the receiver is the same email server as the sender. Let's say in this case, if it's belong to the Gmail receive server, then we send to the Gmail receive server. If it's in a different receive server, we send through the internet to that different receive server. That could be Outlook receive server, that could be Yahoo Mail receive server, that could be XYZ Mail receive server, right? So that's the entire flow for the Gmail backend send service, right? That handles the send part of the problem. Now let's focus on this Gmail receive server or the Outlook receive server that actually receives the message, right? That actually receives the message. Now these servers will actually update the inbox, outbox folders. These will actually update the databases, cache, and a lot of other things, right? Now this is a design for the email receive server on the receiving part of the flow. Let me expand it a little bit so that things are much more visible to us. Okay, now this was Gmail backend sending the message to Outlook receive server. I'll show you which part we are actually. So this part is the client here, Gmail backend sending the message to Outlook receive server. So this link is something which we are actually zooming in, which we are dive deeping. So the Gmail backend server sending the message to Outlook receive server. So definitely the message passes through a load balancer. Load balancer does a lot of things. Some of these are request routing and rate limiting. Now we did some things on the Gmail backend as well, like reducing, validation. But since we are passing through an altogether different receive server, right? So Outlook might repeat the same things again. Whereas if the message has gone through the Gmail receive server, we might not have done the reducer and the validation part. But since we have gone to a separate receive server, we are again repeating the reducer step, storing them to AWS S3, validation step, and other things. All right. Let's say after the Outlook receive server has also completed the validations, it pushes the message through message queue. We are very clear with the concept of PubSub and message queue. It acts as a buffer, enables both the upstreams and downstreams to scale independently. Now, these update consumers, what they have to perform some tasks, right? So what sort of tasks they need to perform? They will update our metadata database. Now what will be stored in a metadata database? This metadata database will store the user folder details, right? For example, user B folder inbox has this new email. User C folder inbox has this new email. User A folder outbox has this new email, right? So these tasks actually update those details into our backend databases. These consumers actually have this task of updating those folder specific details into our backend databases. Some of these details could be updated in the cache as well. Let's say for recent emails that are frequently accessed by the users, for faster fetching could be updated in the cache as well. But let's not go into more detail of cache in this scope because we have much more problems to tackle now. Now, definitely user A has sent the email. We have received the email and updated our databases. But how will users B and C will get to know that they have received a new email, and that too in a near real time? How will that happen? So I think this part is clear, while like this entire straight part how we have updated the database in cache. But the second part that's very important, how users B and C will see the new email on their application, that they have received a new email while they refresh, or even without refreshing, that a new email has arrived on their Gmail or Outlook application, and that too in a near real time. So once we receive one task here, we send that task to a service called, let's say, a real-time service, and this real-time service, based upon the client, it sends the updated message to the client. Now this is very ambiguous. We will dive deep into this section as well, but you understand, like, we got a receive task, we updated it into our database and cache, then we sent to a real-time service. Now from this real-time service, the clients are actually listening for latest email updates they might be receiving. Now you can imagine that for a client to listen to latest updates, the client is supposed to be present online. What will happen if I go offline? Let's say I stop my internet, I delete the Gmail application or Outlook application from my Mac or my mobile or my iPad, I go offline. Then after 10 hours, 15 hours, I come online again. Whereas in between those 10 to 15 hours, I received lots of emails, but I was not available online to listen to the latest emails that have been received by me. How will I capture all those emails that I received while I was offline? So I'll explain this flow, how you will fetch the offline updates. So let's say the client B in our case was not online when A's message was sent. So when A sent the message, B was not online, so B could not receive it real time. Let's say after 10 hours, B comes online. So what will B do is, B will make, the client of B will make a request to a service called fetch offline updates, and this client will tell this service that this was the last message I received for me. So this service will go and check this metadata DB and query that after this time, how many messages are received for B, and pass on those messages to B's client. But let's say while these offline updates are coming for B, B can meanwhile receive the real-time updates as well because B is now online. So B, when it comes online, it will have these two receiving channels. One are the offline old updates, and one are the real-time updates it can receive from the real-time service. Now for some time both of these channels will be open, and there would be a logic at the client end that will handle which emails to show based upon the timestamp. Now after some time, all the offline updates would have been reflected on the client side, and we no more need the offline updates because we have caught up to all the things that we have received in the last 10 hours while we were offline. Now our application is online. We can keep listening on this real-time channel, and if any real-time updates come, we can keep listening to those email updates, and those email updates will be updated on the client B. That's how there are two channels. One is for the real-time updates and one is to fetch the old offline updates. And when the client B comes online, for some time both channels are live, but after some time offline updates have been applied and only the real-time channel is live. So that's how A sent a message, A sent the message to the receivers of Gmail and Outlook. These receivers update the message to their respective databases and send the real-time updates to the clients that get reflected in your applications. You don't have to refresh your application, right? But this part is very important. Like, how do clients get latest updates from the real-time service? And believe me guys, these real-time updates, this logic which I am going to explain you now would be useful into a lot of system designs, be it the system design of WhatsApp, Slack, Messenger, live games like Counter Strike, and a lot of other things. So this is a very important topic, and let's dive deep into it. So from Gmail perspective, this was a prospective design, right? We are just going to focus now on the real-time updates which the clients will actually receive. So definitely it seems to be a very complicated diagram, but before I explain it, let me explain some very important concepts like what is short polling, what is long polling, what is WebSockets, what are server side events. So these are some very important